Okay, let's start, folks. Good morning. My name is Ross Jones, and I'm responsible for improving the practice of systems engineering across the lab. And I want to welcome everyone to our at this month's system engineering seminar. Past seminars have dealt with a couple of technical practices of the emerging new practice of systems engineering. Today's topic is very different, but also related. To be a good systems engineer at JPL, we expect you to be competent in three areas. One is the technical processes of systems engineering, requirements and architecting and verifying and validating and risk management and so forth. The second is to have technical knowledge of your a domain of practice. And then the third area is certain personal behaviors. And today's seminar is all about those personal behaviors of a JPL systems engineer.
A good one.
A very good one. And today's speaker is Gentry Lee. Gentry is the chief engineer for the Solar System Exploration Directorate. Previously, Gentry was the chief engineer for the Galileo project. Prior to that, he was the director of science analysis and mission planning for the Viking project. And so Gentry goes way back here. And then he's old and experienced and wise.
Just old and experienced.
And then finally, in addition to his engineering work at JPL, Gentry has written 7 science fiction novels, and he partnered with Carl Sagan in the design and development of the Cosmos television series. So please join me in welcoming Gentry Lee.
Thank you, Ross. Okay. The reason I'm here today is that there are those people who, every time they talk about systems engineering, start immediately looking at a cookbook and start saying it's process 1 plus process 2 plus process 3 plus process 4. And my statement is, right away, I'm going to be controversial, so pardon me. The processes are to a systems engineer as the tools, the paintbrush, the colors, and the canvas are to the artist. You have to learn how to use them. But if I use the same tools that Salvador Dali uses, you will tell the difference. Okay? And what I'm going to talk to you about today are what are the characteristics that make for a good systems engineer. This is part of your personality. All right? Now, the first one, well, first of all, I guess I should say, because 3 people asked me, what kind of systems engineering are you going to talk about? And I said, anything, it doesn't matter what it is in front of systems engineering. It can be a program systems engineer. It can be a project systems engineer. It can be a flight systems engineer. It can be a software systems engineer. It can be a payload systems engineer. It can be an EEIS guy or girl, okay? All the things that I'm going to say apply to all of those functions. And what is it that makes a systems engineer different? It's a very simple thing. Here is a picture, and those of you who have worked with me for a long time know I like to make pictures that really have no real meaning. I am not Salvador Dali. I have the marker in my hand, and that's all I know how to do. But nevertheless, this is the whole job, whatever it is, okay? And then there are people, I'm going to pick a flight system as an example. This person is responsible for the mechanical subsystem. This person is responsible for the electrical subsystem. This person is responsible for the software, and so on. What is the systems engineer responsible for? Everything, okay? That's the first thing you've got to know. When you talk about, if you have systems engineer in your title, your province is the world, or it is the inverse of everything everybody else is doing inside the world, depending on what you want from a set theoretic point of view. So what? I'm going to list 10 characteristics like David Letterman does. Oh, there's a seat over here for you, for who's next to my son. Okay, they are prioritized in some general sense, only that one is more important than 10. But let's not get into a risk management, what cell of the matrix these things belong in, please, because they're more or less all right. The first one, the most important one, the sine qua non of any good systems engineer is intellectual curiosity, okay? If you've never asked the question what, why, or how, don't take a job that has systems engineering in it, okay? This is absolutely a characteristic of this kind of a function, and you can't do anything other than that. And I'll also use moving into contiguous vacua. This is the way you define these people. As young people begin in their careers and they come up, there are those who, like the horse with blinders on in the race, say, this is my job and I'm comfortable here. And there are those who say, well, I understand more or less what my job is, but what's on the frontier? What touches me? And they go out there and say, that's interesting. And then a little farther, and ordinarily what happens in this situation is somebody notices. And they say, well, maybe this person can do more than that first thing they're doing, and so forth and so on. So that's number one. Number two, the big picture view. Boy, oh boy, oh boy. This has several dimensions. First one I'm going to give you is what I would call the programmatic view. A good systems engineer understands that from concept through operations, there is a significant role for systems engineering throughout, and more importantly, that it changes as the process goes on. But if you're a systems engineer, you begin your task wherever you are in this general phasing with full knowledge of that which has been done and was necessary and that which must be done in the future. In the conceptual phase, it's mostly trade studies. That's the focus of systems engineering in the conceptual stage. In the operations stage, it's making sure that the mission requirements are met. In between, you have a preliminary design review, a critical design review, a testing phase, launch, and operations. And each step has a different emphasis for the systems engineer, and the good systems engineer knows this. In this stage, you're still doing trade studies, but you're coming down to developing the top-level requirements, then flowing them down so that the requirements are finished at this stage if they are done correctly. And of course, later on, I'm going to say one of the things you have to be able to do is to be a good system engineer is live with change, which means they won't really be finished there. The next part, and this all in here, is validation and verification. Now, what do those things mean? Well, we have developed our own argot in the engineering business, and so it doesn't matter what the dictionary says verification and validation means. What we believe in the Jet Propulsion Laboratory is that verification is proving that something meets the requirements that were written for it. And validation means that the spacecraft can do what it's supposed to do, whether the requirements were written properly or not. Don't go to the dictionary and don't have a discussion with a non-engineering person about what those words mean, because it's irrelevant. This is our world, and we'll use the words that we would like. And so therefore, we go on from there. All right, next, big picture view. This is very important. What is it that we do here? Now, I ran this test on a half a dozen engineers who did not know I was running this test. Okay? Now, try it. Just go ask somebody who's not here today, what is it we do here at JPL? And just listen to the variety of the answers that you get. Let me tell you that a good systems engineer understands the following picture. There are questions, fundamental questions about the nature of the universe. Now, this is limited mostly to what we do here. The next thing that happens is there are hypotheses. The scientists look at the questions and they say, well, I have a hypothesis about how things ought to work. The next thing someone says is, how do I test those hypotheses? What follows after that is measurements. After the measurements come data, and in this process, we are down here trying to derive the means by which the answers to these questions can be determined as unambiguously as possible. That's what we do here, okay? We only exist. Sorry, I know engineers don't like to hear this, but we only exist because there are fundamental questions about the nature of the universe that someone is trying to answer. A good systems engineer is completely conversant with what the questions and hypotheses are on the project that he or she is working on. If you are not, you don't get it. It's that straightforward. So, the next one follows very straightforwardly. Connections. Rob Manning has heard me on this subject for a long, long time. A good systems engineer basically can do a barium trace of his or her entire project with whatever the input is and determine, someone says, here comes X, and a good system engineer immediately in his or her mind takes X, flows it through the project, and knows every soft spot that responds to that X. That's what the systems engineer and the glue is all about. Now, there are techniques for doing this. One of them is what's called the N-squared technique, and I have recommended to young systems engineers or systems engineers doing this for the first time that they formally go through this. Some of the people, like Rob, have been around a long time. This happens automatically when you do the process, which is basically you build a matrix, and it goes like this. And you put the items across the rows and the columns so that you have basically down the diagonal is a void. And I'm going to just pick the same example I used before: mechanical, electrical, payload, etc. Just software, list everything here. You do the same thing this way. And what you do is you say, okay, what comes out of this and goes into that? And then on the other cell of the two, it's what comes out of that and goes into this. This is an excellent tool for people to understand, to make the first step in understanding the connections. I have worked recently on several projects in which I've been asked with a team of very talented people to figure out how to help get things ready for a major event, I guess is the best way. And I have discovered that understanding this process is not universal. There are people who operate on a particular subsystem, and no one has ever told them that after they put out whatever it is they do, I'll just take an example, a star tracker, which goes into an attitude control system, which goes into an attitude estimator, which then on deep impact is used to determine how to hit the comet. And if the person who's doing the star tracker has never done an N-squared thing, and no one has ever done it for him, to show that there is a response over there on whether or not you hit the comet based on what comes out of the star tracker, then things won't work. Now, I've heard some people say, well, what are you talking about? If the requirements are properly written, this won't happen. Hello? Okay? There has never been a project in history for which any set of requirements has covered the actual meaning of what needs to be done. Okay? Requirements are an approximation using the inefficacious language of human beings, okay? They need to be expanded. But fundamentally, here we go. One of the things always attributed to me, what are we talking about with connections is basically this. That's it. The good systems engineer knows the partial of everything with respect to everything. Okay? No, I'm absolutely serious. That's what the picture was that I was talking about, and that's what you have to be able to do. You have to realize that if the attitude control system slumps down, cannot meet its requirements by some amount, immediately what does that do all the way at the other end? How is the integrity of the scientific inferences affected by that change? That is the job that is necessary to do. And I will say this, if I had to define one place where we fall down as a discipline at the Jet Propulsion Laboratory, it's that we believe the partial derivatives stop at the science interface. It goes all the way into, now, somebody told me the other day, that requires me to learn a lot about science that I don't know. Hello? That's what our job here is. If you're working on the Kepler program and the job is to locate Earths around other planets, around other stars, and you don't understand the relationship between the sensitivity of your particular device and that final outcome, you missed it. You're not doing what you're supposed to do. If you're working on MSL and the job is to do analytic sampling to determine the habitability that's there, and you don't understand the relationship of the sampling system to the inferences that the science instruments are going to make, you aren't doing your job. Okay? Next. Oh boy. Comfortable with change. Oh boy. Okay. One of my very good friends said to me one day, "How do you sleep at night?" And he said, well, I said, "What do you mean?" He says, "How do you know when your job is done?" I said, "It's easy, it's never done." So I'll go back to question one. How do you sleep at night? I said, doesn't the cue just keep popping up? I said, "No, I control it." He said, "Well, how do you do that?" I said, "I have a glass of wine." No, really, I mean, whatever's necessary to do. I have it under control. There are people who don't realize that the paradigm between being successful at work and being successful at a place and successful at school, these are different. Do you remember how wonderful it was when you were in graduate school and you had an assignment for the week or whatever it was? You had to do 66 boring problems, 66 problems. And when you got to 64, you started breathing a little lighter. And when it was 66, hot damn, I'm done. You don't want to be a systems engineer if that's what you need in your life. You want something nice and circumscribed, okay? Now here is a big personality difference, okay? I can, in a short order of talk to people, I can determine whether or not they are type, I'm going to just call them O and P so that there's no, pejorative here. Type O, a type O person that says, "Let me clearly define in my hypersurface the exterior boundary of my job." Okay? And I will operate inside it. I will do everything necessary, and I will know when I'm done. Okay? That is exactly what we don't do if we're good systems engineers. Okay? Now, so how do you operate? You operate as a good systems engineer operates with an interrupt-driven mechanism. There's no question about it at all. Your things to do list is prioritized. And if Farouz calls you, more than likely it's going to be changed after he calls you, okay? And you just simply deal with it. And when it's time to go to bed at night, you don't give yourself a score. Oh my. You simply say, "I did as well as I could have today, and tomorrow I know I will have to reprioritize." The best systems engineers know that. Now, on top of this, what happens as flight projects evolve is bumps occur. Requirements cannot be met. Someone wants to change what it is we're doing. A discovery is made. Have you ever seen people panic? On the Galileo mission, when I was the chief engineer, halfway through the design cycle, scientists proved that particles of sodium and oxygen that were coming off of Io were getting caught up in the magnetic field of Jupiter, being sped up, becoming highly energetic, and guess what? If they went into the processors and the electronics that we had, they would cause single event upsets. A very, very bright attitude control engineer came running into my office after the discovery. He says, I don't want to do it again. We had to start all over again. We had to throw everything out. We went to Sandia. For those of you who are old and in the audience, we began at the beginning at CDR and started completely all over. Change. It's one of those things. Next, comfortable with uncertainty. Oh boy, now this has two meanings, okay? There's one level of meaning in which you don't know when you're going to finish. You know that the requirements are not complete. You know that there's going to have to be some interpretation. But I mean another thing here too. Someone asked me, what single engineering or mathematical discipline is most important for a systems engineer? And I said without batting an eye, probability and statistics. There is no question about it. And as you deal in systems engineering, you can quickly separate the people who really understand the underpinnings of probability and statistics from those who do not. And so if you want to know something that you might study, being able to define and understand probabilistic statements. Now, let's take a number of different examples. Some of you may have heard that in a meeting last week, I referred to something that was being presented as a bullshit covariance, okay? Now, pardon me for those of you who are seeing the DVD, but that's what I said, so therefore that's what it is. And what that was that I and some of the other people in the group realized that what was being presented to us as statistical information was not, it just simply had no foundation in real probability and statistics. It was an artifice. But if I had not had the good fortune to have been schooled at great length in probability and statistics, it would not have been quite so apparent to me. So this is one level of uncertainty. Now, the second part is even more. It's the uncertain uncertainty. Now you're going to say that I sound like, what was the Rumsfeld talking about unknown unknowns? Okay, I'm going to differentiate between two things. A covariance analysis produces statistical information which, if properly posed, has statistical meaning. Okay? Then there are uncertainties that you have no clue about the statistics. Let me give you a couple that we deal with every day. One is the atmosphere of the planet Mars. I had a lovely young lady come into my office one time and say, to make the following statement to me. Because it is known that the dispersions about the mean of the major atmospheric parameters of Mars is distributed in a Gaussian manner, comma. I said, what? Who discovered that? Let me give him the Nobel Prize. And it turned out that she did not know that there were other statistics other than Gaussian statistics. And in this particular case, the design she was working on changed as soon as I explained to her that it might be uniform. It might be almost anything, and you have to be able to accommodate that. The comet Tempel 1 is uncertain, okay? We do not know where the jets are. We do not know what its albedo is. And the systems engineer who deals with a problem like that has to understand the difference between making an assumption about Gaussian statistics and really accommodating the true uncertainty. That's why I say comfortable with uncertainty. It means two things in two different dimensions. Now, at this point, what I would like to do is I would like to take an example of an extraordinarily challenging systems engineering problem that's going on right now. In talks with some of my colleagues, they said, don't pick examples from 20 years ago. People who don't care about those. Pick things from projects that we're working on right now. For those of you who aren't part of the Deep Impact Project, on the night of July the 3rd, if all goes well, we are going to strike the comet Tempel 1 at 23,000 miles an hour. And it is a 14-kilometer long and 4-kilometer thick device that we are closing in on, yes, that's right, at 20,000 miles an hour. It's like a bullet hitting a bullet with another bullet watching, okay? Except it's worse than that. Okay? Now, one of the most difficult and intriguing systems engineering problems that I have ever encountered in my life is the one of the impactor targeting system. But for those of you who don't know this, 24 hours ahead of the time they reach the comet, the impactor and the flyby separate one from the other, and the goal of the impactor is to hit the comet. The goal of the flyby is to take a photograph of the impactor as hitting the comet. And if the impactor hits the comet, but there's no picture of it, it's like a tree falling in the forest. Does it make a sound? Okay. And if the flyby takes a picture of the comet, but the impactor doesn't hit it, that's not too good either. Anyway, what has to happen on board the impactor is the following. It has to figure out its attitude, figure out where the comet is, make maneuvers to get rid of any error in where it is with respect to the comet, and make up to 3 maneuvers, and then finally hit the comet. Now, how many different skills do you have to do this job correctly? You have to understand attitude control. You have to understand, among other things, navigation. You have to understand how to process photographs. You have to model the uncertainties in comets that spew and have dust. They may have this albedo. You have to take all of those things into account. You have to know camera characteristics so that you don't respond to the wrong stuff. You have to know and put into the intelligence of the spaceship. This is a true state-of-the-art, cutting-level systems engineering task. And there are not many places in the world that would even attempt it. But we are attempting it, and we're only 30 days away. Next, that was a good lead-in. The next characteristic is proper paranoia. All right, now you'll notice that I have picked a modifier that's very important. There are people who are like Chicken Little, and they run around saying, the sky is falling, the sky is falling, all the time, okay? That's not proper paranoia. Okay? Proper paranoia is, the sky is falling, I think. Okay? Specifically, for you young engineers, please, please do not be offended by what I'm about to say. But many of you were the brightest and best students at the brightest and best universities. You are used to being right. Okay? The professors told you you were right. The back of the book told you you were right. You graduated summa cum laude. You must be smart. Heh. Okay. I wish I had a nickel for every genius or near genius who, after graduating from Caltech or MIT or way below normal or wherever they came from, suddenly, maybe in their late 20s or their early 30s, did something at a place like this and it didn't work. Oh my gosh. Systems engineers are properly paranoid. While all the subsystem people are running around saying, I've got it, the system engineer says, does she really? Does he really? And there leads to 2 very fundamental disciplines. Someone asked me one time, if I want to be a systems engineer, what is my best practice job? Now we get into a discussion that I've had with many of the people in the division. Does a systems engineer have to have delivered something first, either hardware or software, before they can ever really be a good systems engineer? The answer is most of the time. Okay? There are these people who, like Zeus was from his mother's womb untimely ripped, but most people should do this, okay? But nevertheless, after that, where do you start? And I will tell you where it is. It's in fault protection. Fault protection is the single arena, as far as I'm concerned, of engineering in which the systems engineering attributes are required before you become fully responsible for systems, for the whole task. And I have noticed this over many, many years, that the kind of thinking that goes into fault protection is dominated by proper paranoia, if you've got it right. Now, I want to use an example of something that happened recently to sort of underscore the importance of proper paranoia. We have in our litany something called a critical sequence. A critical sequence is defined to be a time when, if the spacecraft does not do something that it must do at that time, the mission is over. And so the design takes great liberties to make sure that if anything possibly can be completed, it will be completed. Standard things like this are for Mars orbit insertion, you know? You don't insert, hello, the mission's over. And so forth for Jupiter orbit insertion and other such things. We have critical sequences in all missions. If you are properly paranoid, when you design a critical sequence, you say to yourself, I am going to do only those things that need to be done to get me to a safe position. And once that is done, I will stop driving my spacecraft in a way I would not want to do it otherwise. Now, in the last 5 years here, I have seen 3 examples where that principle was violated, where the designers were not properly paranoid, and they said, well, while I'm doing this, I might as well do this. And they forgot that while they're doing the second part, which was not absolutely necessary, they could have done damage to the spacecraft. And so, again, that's where this proper paranoia fits in the overall scheme of things. The next thing I would like to talk about are resources and margins. And I realize that now I've violated, there's not order in the syntax of this entire list, but forgive me for that. A good systems engineer keeps in his or her mind at all times a running score of how the resources of the project, that's power, mass, delta V, whatever it might be. But more importantly, that's easy, knows the margins. Okay? What exactly do I mean by a margin? If a spacecraft must do something, okay, you suballocate requirements. There's one kind of margin in the fact that you make the requirements a little tougher than's absolutely necessary to meet the level 1 requirements of the mission. But I'm not talking about that. Some people call that contingency, and I'm not going to get into a big discussion about words here. What I'm talking about is the difference between, in a hypersurface sense, requirements and capability. Okay? These are the requirements. And after they're all done and you go through all the testing, if the job has been done correctly, you have a capability. And I'm making it touch over here at one particular point on purpose. The systems engineer during the test and operations phase must know this in multiple dimensions by heart, because things will change at all times. Now, we had on MER an absolutely perfect example of the importance of this concept. And it is why it is not sufficient, systems engineers, to simply know your requirements and say, whoop, we met our requirements. What can happen is that these things, what's in the bag in here, remember this, knowing the partial derivative of everything with respect to everything, they can be shifted around in case this sort of thing starts happening. And you need to be able to make that. And in the entry, descent, and landing, for those of you who have never touched that wonderful thing, it is absolutely essential that from the beginning you realize that you're dealing with things that are not, as you're dealing with soft goods, parachutes, things like that, that you have to be able to understand the difference between the requirements and the capability. Now, some of you may know that we changed the dynamic pressure of chute deployment on both MERs in the last week before we got there. And if we had not both known this and known the partials, that would have been impossible. We're getting down the list. Communication skills. Okay, folks, you cannot be a good system engineer if your goal in life is to sit in your office. Okay? It's not working. It doesn't happen. The systems engineer has to be both a transmitter and a receiver. Hello. Okay? That requires that you have, I'll get to another thing a little bit earlier. I was told by one of my friends one time that so-and-so, it was part of an evaluation process, was a tremendous speaker, but he never listened to anything anybody told him. That doesn't do the job. Doesn't do the job. The next one is self-confidence and energy. Now, I guess you could point out to me, if you wanted to be, doing partials with respect to things, that it would be pretty hard for you to sit inside your office if you had energy. But nevertheless, I view these as two different things. Now, what do I mean by self-confidence? Simply the ability to know what you know and to know what you don't know and to not be afraid to hang on to those two things. There are two sets. A, the set you're comfortable with, you know. A inverse, you don't know that. And you deal with those. Self-confidence is not arrogance. Okay? I must remind people at this institution of this over and over again. Okay? Even we are sometimes wrong. Even I am sometimes wrong. Okay? Now, this particular characteristic is very, very important because it leads to one of my fundamental statements. Commission, not omission. This should be written on the door of every systems engineer. There is no excuse for omission. You do not, if you are the systems engineer, you do not need authority from anyone to investigate anything. If your project manager thinks you have stepped on his or her toes, believe me, he or she will tell you, okay? And to sit there and say, I didn't do that because nobody told me I was supposed to, sends me into orbit, okay? The job is the whole space. You go out, you make decisions. If someone tells you to stop, then you go to number 8 and you listen. Okay? But that's it. Finally, the last one is appreciation for process. Now we've come full circle. We're back to where we started. I used the metaphor of the paintbrush, the paints, and the canvas. And I pointed out that I could go to school along with Salvador Dali, and probably at the end, none of you would buy anything I was doing. And that is an apt metaphor, but it's too harsh in the following sense. You can't do your job without the canvas and the paintbrushes and the colors. And so those who say, I don't need all that crap, okay, are just as wrong as those who say, if I know that crap, I'm a systems engineer. Neither one works. And as I told Ross several times when we were having this discussion, you have to understand the process. You have to appreciate the process. But that which differentiates between the good and the great is personality, personal characteristics. A wise friend of mine once said, in the middle of the 20th century, he was nominated for a Nobel Prize in Science. In the middle of the 20th century, this was a long time ago, a man or a woman who knows nothing but science is a bore. A man or a woman who knows no science is ignorant. This is what I tell you, budding systems engineers. A systems engineer who knows no process cannot possibly do the job. A systems engineer who knows nothing but process is not much better. Okay? And that's where we are. Now, one last thing I want to leave you with. Why do I believe that talking to you about this sort of thing is so important? If I had to define the one place in this institution that worries me, the one attribute that worries me the most, it is that I do not see the next generation of people who can be good systems engineers on billion-dollar projects coming up. There's not enough of them. There's not enough people, what I will say right now, getting ready to do this job. It is challenging. It is exciting. It is fun. It is rewarding. If you're interested in this, I suggest you talk to your management. We have plenty of places here. We have a training program that we're going through to try to build the capability here. And finally, somebody said to me, "Why are you always so enthusiastic about everything?" And I said, let me tell you something. I've spent a lot of time in this world, and not all of it here. I've been out and I've done things every place else. And there is nothing like where we work to have, first of all, both the intelligence and the integrity of the people around us is as high as, I can't even imagine it could be this high anywhere else, and certainly it's much higher than any place I have ever been. But in the final analysis, what do you system engineer? What is the end product of what we do? I was asked on television just 2 weeks ago, what do you do? I said, my job is to add to the knowledge of the world. That's what we do. Thank you all very much. I've just been told we're going to have questions and answers. For those of you who need to run, that's fine. So,
Sure. So any questions for Gentry? Okay, there's one over there.
Gentry?
yes. Hi, Tom.
Hi. You made it sound in your conversation, you lean very, it's going to sound strange coming from me, but you lean very heavily on sort of one person knowing everything. And I feel like one of the things I've learned here working on the lab is that really what you want to do in something like system engineering is have a team of people work in groups, because one person can't know the necessary level of detail to be able to answer all the kinds of questions that you want to ask when you're doing system engineering. I don't think you disagree with that.
Not at all. I completely agree with that. And if the inference, if the implication in what I said was that this was a solo thing, then thank you for making that correction.
Another question or comment?
Yes?
I'd like to make a comment. If you look at all the job descriptions for employment at JPL for engineers, system engineers of various types, what the requirements are, you never see any of this on the list.
Next question. Okay, take care. Oh, okay, yes. Hi.
You raised a point about the next generation of multi-billion-dollar systems engineers.
$1 billion.
Billion-dollar, okay. Well, how do you see the skills for a billion-dollar mission systems engineer versus smaller ones that the lab has a multitude of now?
I believe that the jobs are similar and we're lacking in both categories, except that, and you'll have to pardon me, I'm wearing my institutional hat right now. A $1 billion failure is bigger than a $300 million failure.
Yes.
Okay.
Another question? Brian.
Brian.
Gentry, how do you make up for a lack of system engineering quality, for example, say, in one of our contractors, someplace where we have some sort of relationships that requires us to be careful?
I'm being taped on a DVD that's going to be sent all over the place.
Okay.
I believe, watch this. This is a little political footwork. I believe that those of us engaged in the frontier activities of creating knowledge should share our systems analysis experience and processes. How is that? Wouldn't want to appear arrogant. Self-confidence, all right, but not arrogant. Yes, Chris.
This might be a two-pronged philosophical question.
Oh my gosh.
One, I guess, in standing up there and orating on our knowledge of system engineering and how we have defined this undefinable job, what are the dangers of thinking that we are understanding what it is, and the demons that are lurking by thinking what we know what our job is? And then the other thing, in the modern sense of email and telecoms and all that type of stuff, what are the modern plagues of system engineering?
Okay, the first question goes directly to number 6. I once wrote this: proper paranoia and a little bit of schizophrenia. Okay? Because if you never believe you have the job under control, you never will have the enthusiasm to try to do it. But if you ever think you've got it under control, the next day, I guarantee you, something will come up that you hadn't thought of. So I think if you balance these things off, and as you go through your job, and Chris is, for those of you who don't know, is a flight system engineer on Phoenix, you have to acknowledge at the same time that you're doing everything you think you can, and it's probably not enough. And that gets back to being comfortable with uncertainty. There is no way, folks, this is terrible to say, there is no way, and you have to tell your spouses this, that a good systems engineer on a JPL project ever goes to sleep at night comfortable. It just doesn't happen. It can't be. Does that help you? No? Well, you asked me what about, the first part was about whether or not you could get over confident.
Yeah, no, I mean, yes, and no, it doesn't help.
I understand. You learn to live with it, you know. It's one of those things. And the second part of the question?
Plagues of electronic communication.
Well. Okay, folks, you're now going to see some of my idiosyncrasies. Number 1, people should attend meetings. If you don't need to be at that meeting, don't come. Okay? Don't sit there, flipped out, inside your computer, reading your mail, and when someone calls your name, go, huh? Okay? Now that's me. I've been told that I am an absolute anachronism where that's concerned, but I do not like to be calling on people in meetings and asking their opinion only to discover that they're doing something other than that altogether. The second thing, email does not substitute for face-to-face communication. Email, okay, it is a slow, non-interactive process, and most of the things that we deal with in systems engineer are what we would call interpretations. They require, as Fruz and I sometimes will talk for 15 minutes before we really understand what it is we're saying to each other, and we go back and forth, a dozen times in between. That email route would take weeks, because that's what it is. So a systems engineer who relies, now this gets also back to working with contractors. I know people don't want to go live somewhere else, or they wouldn't be here. Okay? And I know travel is a pain in the butt. But if you are the systems engineer for a contracted mission, I will guarantee you, if you are not spending at least 25% of your time, and preferably more, face-to-face with the people doing the work, you can't do your job. Yes, Fruz?
I assume there's some people sitting in the audience looking at the list of 10 here, and they're asking themselves, well, how many of these applies to me? So the question here is, in your opinion, are most of these acquired or mostly inherent in the person? And depending on which way you answer that, the next question is, are system engineers trainable? Do they come out of it?
All right, that's a very, very good question, and I will try to give you my answer. First, if there's no raw material, forget it. Okay? Now, that's just the way it is, you know? I mean, I hope no one here thinks this is a pejorative comment about newspaper delivery boys, but my newspaper delivery boy could not be a systems engineer. Okay? I've had 4 or 5 conversations with him, and he's perfectly good on such things as what day is the first of the month, because that's what I'm supposed to pay him. But he doesn't have the raw material to be a systems engineer. On the other hand, it is likely that as many, assuming that JPL's personnel policies have some logical sense, and those of you who want to deal with that one, it's not happening here. But at any rate, probably 3/4 of the people at the Jet Propulsion Laboratory could be systems engineer if they want to be. But some of these characteristics, I'm telling you, some of them are very difficult. This one right here, comfortable with uncertainty. It's a fundamental personal characteristic I've noticed about people, that if they don't have their things to do list completed, at the end of the day, their psychological state is in chaos, okay? And it's true. I mean, once upon a time, 20 years ago, I took one of the brightest young women I have ever met in my life. She was a PhD from MIT. And I tried to teach her to be a systems engineer, but she was an organization freak, okay? If you went into her apartment, okay, we won't go there, but if you did, okay, you would find that everything was in perfect order. One night while she was getting dressed, I picked up the remote control and I put it back down, and the TV was turned on and off only for a short period of time, and when she came out, the first thing she said was, "You've been watching TV." I had moved the remote control at least an inch. Nope, she couldn't get there. I mean, it was impossible. We tried. She was brilliant, but she would just lie there at night, she told me, staring at the ceiling. Staring at the ceiling. So to answer Firuz's question, most of these things, most of them can be learned, but there must be some raw material, and the raw material includes a certain intellectual ability and a certain flexibility of personality. And since many of you have 1 o'clock meetings, I want to thank you again. This was great fun.